Hello students, hopefully you must be enjoying whatever all we have discussed in kinematics. So this is being the last part of this particular topic. We have already understood about the relative motion between two different objects. So the two objects can either be moving or it can be at rest. Either of them can be at rest. We are now going to generalize that to the concept of curvilinear motion. What does curvilinear motion actually stand for? When the object is moving in a curved path, for instance, let's take the case of a car moving in a curved road. When the car is moving in a curved road, obviously, even though its speed may be constant, it may be moving at a constant rate, but its direction is changing at every instant. Since its direction is changing at every instant, so therefore, that velocity is changing, and therefore there is a force acting on an object. So taking the cue from this, we'll understand about curvilinear motion in this last part. So what do we understand about the other type of motion? Let's say talk about the curvilinear motion. So talk about the curvilinear motion when the particle is moving along a curve, not in a straight line. That is what is meant by curvilinear motion. So its velocity is changing at every instant of time because it is moving. So therefore, it is going to be an accelerated motion. In this case, what we are going to say that the position vector of a particle at time t is going to be defined by a vector with an origin O. So if I say that this is the vector, this is the origin. So at every instant of time, if I say r is the position vector of the point P, r prime is going to be the position vector of point P prime, and so on. So as a result, what we are going to say is that it's going to be the position occupied by the particle at any instant of time. So if I say that, if I consider that the particle occupies a position P, which is given by some displacement r at time t, and P prime is given by r prime, in that case the velocity of the particle P can be given by delta r by delta t, which is nothing but in the limit delta t equals to 0, so this is going to be equals to dr by dt, which is nothing but the instantaneous velocity. That similar manner we can say that delta s basically is not the displacement, it is the distance. So it is starting from this particular point, let's say. So from here to here, how much is the distance it covers? So this is how we find out the instantaneous speed. As you can see, this is with an arrow, so it's a velocity. So it is going to depend with respect to the position vector from the origin, mind you. Right? Let's go further and try to understand further about it. So when we talk about this, so what we are going to say is this: if we consider the velocity v, sorry, it has gone off. At the time t and the velocity at point v prime, in that case we are going to find out the acceleration. So this is the value of instantaneous acceleration. You know that there is no possible instantaneous acceleration in a scalar quantity. There is nothing defined as acceleration, analog of acceleration in scalars. There is nothing. The reason being, acceleration comes from force, and force being a vector quantity, acceleration has to be vector. There is no other quantity, right? Okay, let's take it further. So when we go further, we will say that in general, the acceleration vector is not tangent to the particle path and the velocity vector, because it goes like this. So it's going to be as a resultant. So taking it further, what we will say, if I say that the point P, which is a vector which is function of any variable scalar u, so I can simply write it down as, so this is nothing but from the first principle. So from the first principle, we can write it like this, right? Hopefully this makes sense. And therefore, if we go further on this, we can simply say that the derivative of the vector sum that we have, so if we have two given points between P and Q, just from the simple concept, we can write it like this. So any two given vectors, if you want to find out the derivative of any other variable u, it's going to go like this. The product, in this case, product of a scalar and a vector functions, mind you. So one is going to be a scalar, so f is small f is a scalar. So when you are differentiating, you have to differentiate both. So you differentiate first the scalar, keep the vector constant, then you differentiate the vector, keep the scalar constant. Okay, now the dot product and the cross product. So the rules are going to remain the same. The dot product in this case, so you differentiate the first vector, keep the other vector as constant, and then you have to put the same sign, that is, if it's being dotted or crossed, so it has to remain as dotted or crossed. Neither you are going to change the orientation. If you change the orientation, obviously that implies that you are also going to change the sign of it, because these are all vector quantities. Okay, let's take it further. So if any point here is point P, so the position vector of that particular point is going to be given by the three vectors, which you obviously must be knowing, and vectors you would have done. So you'll have xi, yj, zk, so x, y, and z. So these are the three components. These are the three values that exist along I, j, and k directions. I, j, and k are the unit vectors along the three directions. In a similar manner, when we talk about the velocity vector, so for the case of velocity vector, we are going to say the velocity v is going to be given by dx by dt with I, dy by dt with j, dz by dt with the factor k. So this is nothing but the value of the velocity along x-axis is the value of velocity along y-axis is the value of velocity along the z-axis. So if I write down in terms of component vx, vy, vz, these are the values of the velocity. In a similar manner, I'm not going to go into that. These are the values of the acceleration that we have. This is how the acceleration is going to be. Okay. Now, in general, what we try to do, we try to break up the values or the components into different parts. So when, let's say, if I throw any particle with respect to making it some angle with regard to the horizontal, so at any instant of time, the vertical height reach is equal to y. So we'll say that the acceleration along the x-axis is going to be 0. There is no force acting along the x-axis. The force acting along the y-axis is there, so that results into a negative acceleration g, that is along the ground, and there is no acceleration along the z-axis. With the initial condition being there are no initial values of displacements x, y, and z as 0, and the initial values of velocity are these also 0. So if we integrate it twice, so this is going to give you the general equations. So once you know about the general equation, final value of velocity along x-axis is not going to change because there is no acceleration, so it is not going to change. There is going to be a change here along the vertical values of velocities. So along z-axis we are just concentrating on a two-dimensional motion, and that gives us this, and integrating further is going to give you the values of the displacement. Here we are assuming that the motion taking place along the horizontal direction, that is the component along horizontal direction, is uniform. There is no frictional force. We are not taking into account any air resistance here. Either since it is not touching the surface, so there is not going to be any frictional force either. The velocity or the motion along the vertical direction is uniformly accelerated or uniformly decelerated, howsoever you like to put it, because it is being acted upon by the force of gravity in a downward direction. So this is nothing but the projectile motion that we are referring to. Okay. So the motion of the projectile could be replaced by two independent rectilinear motion. You can say that there are two motions taking place simultaneously, one along horizontal, the other along vertical. Once you know the values of the two things, you can write down using the vector components, and then you can find out the resultant of those. Okay. Going further with this, if you want to say that, if you want to find out how one object is moving with respect to another frame. So if there is a translation of the frame itself, reference frame itself, in that case, for that you first need to identify your reference frames. So let's say this is one reference frame that we have. So you designate one frame as the fixed frame of reference, and all other frames are not rigidly attached to the fixed frame. They are going to be moving reference frames. They are going to be changing. They are going to be moving with respect to the first one. So in this case, if I try to say that the position vectors for the particles A and B, so here what we have, this is the particle A that we have, and this is the particle B that we have. So in this case, the position vectors for particles A and B with respect to the fixed frame are, let's say, RA and RB respectively. So the vector RBA, so that is going to be nothing but the change in these, so that is the relative position of the two vectors or the two quantities. So if you want to find out, like we had done previously as well, so RB can be written as RA plus RBA, and if we differentiate it twice, it's going to be giving you the relative velocity of B with respect to A, and similarly relative acceleration of B with respect to A. The absolute motion of the B can be obtained by combining the motion of the object A with the relative motion of the B. So that will take into account the reference frame movement as well. Okay. Taking it further, we can say that the tangential and the normal components, so there are going to be two components. One is going to be a tangential component like this, and the normal component is always going to be directed towards the center of motion. So when the velocity vector is tangent to the path of the particle, in that case we say that the acceleration vector is not going to be tangent. If you want to write it down in terms of the tangential and the normal components, you can write down with respect to the origin. So let's say,
So when you try to draw it with respect to the origin, so this is basically the change that has taken place. So let's say ET is the original position vector, ET prime is the final position vector, and as a result, delta theta has been the change in the angle, which results, or using the vector formula, you'll say that ET plus delta ET gives you the ET prime. That's the reason you have this very. So if you use this, if you try to write down in terms of component, you can write down in terms of component like twice of sine delta theta by 2. Under this particular relation, you can say that the normal vector value is going to be dEt by d theta, because it's going to vary along theta itself. That was the normal component. So here what we are trying to write down, we are trying to write down irrespective of our system of units, right? So that's the reason we have defined these unit vectors et and these vectors et and so on, and that will help us in finding out the values along the tangent and along the normal, right? Okay, so when the velocity vector, you express it in terms of like this, the particle acceleration may be given by something like dv by dt, which is equal to dv by dt into et, where et tells you about the direction. So these are nothing but the variation of the vectors dEt by d theta, so that gives us this, and so on. So if you substitute all these values, here, so that is going to give us the values of acceleration at, the value of the normal acceleration. So this was the tangential acceleration, this is the normal acceleration. The normal acceleration basically comes from the centripetal value of force. Even if you substitute it out here, because everywhere it's the dE by dt, but E basically does not vary directly. It's not an explicit relation with time t. So what you do, E, as you know, varies with time with theta, and theta varies with the displacement ds, and ds varies with time. So if you plug in all of that, so that is going to give you the v square divided by rho. So if you substitute all of that, so that is going to give you the tangential component of the acceleration. The tangential component of the acceleration is going to reflect the change of speed, and the normal component reflects the change of direction. It's a very, very important thing. So tangential component of acceleration reflects change of speed, right? And the normal component reflects the change of direction. So this is how it works. Okay, going further, what will we say? That the tangential component may be positive or negative. The normal component always points towards the center of curvature of path. That is, it's always going to be pointing out towards the center. If you want to write down the relation, as we found out the values of the acceleration. The acceleration is dv by dt, so this is along the tangent. This is the value of velocity, this is the value of acceleration along the center. That's the reason you have the normal value. So at, that is the tangential value, and this is the value of normal. So the plane that is containing both the tangential and the normal unit, so this is what is known as the osculating plane. So this is always going to be lying within a particular area, right? And using this, what you will get that the normal to the osculating plane is found from this particular relation. So En is going to be the principal normal, Eb is defined as a binormal. So that's going to be the resultant value of En and Et. So these ways help us in finding out how any particular particle can be expressed in terms of its components. So hopefully this made sense in understanding as to how it works, how you can use the normal component and the tangential component with regard to our cases. In case you have any doubts in whatever we have discussed, please feel free to ask your doubts. For that, you need to go to www.askIITians.com. In that, you need to click on the discussion board. Once you click on that, you will find an option of Ask Experts. In this, you can select your category out of the categories that we have out here, and then you can post your question. We experts at Ask IITians will get back to you with the answer within 24 to 48 hours.
So students, we learnt about the curvilinear motion. When a force acts on an object, the body does change its direction as well, like it changes its state. So in the case of curvilinear motion, when the object, even though it may be moving at a constant rate, can change its direction. So that is what we learned about in the case of curvilinear motion. We also understood about how the equations are affected in the case of curvilinear motion. To put it on a broader perspective, in the whole chapter of kinematics, we learnt about how any object, when it's changing its position, what exactly is the motion of an object. How are the different quantities that we find, that is the initial velocity, final velocity, displacement, acceleration, are affected with time. We also found out with a graphical as well as an analytical method what are the relations between these quantities, right? Finally, we generalized that in the case of curvilinear motion. In the case of curvilinear motion, we understood as to what is the relative motion concept in linear motion, how it can be generalized for the case of a curvilinear motion, what are the forces that act in the case when the body is moving in a curvilinear path. Hope you enjoyed this whole chapter. Please stay tuned and try to listen to other lectures on physics, chemistry, mathematics and biology on askIITians.com.